Based on magnetic susceptibility and relative magnetic permeability of materials, they are classified into three categories, namely diamagnetic, paramagnetic, and ferromagnetic materials. Now, let us discuss the properties of these materials, starting off with the diamagnetic materials. Diamagnetic materials are the materials that are repelled by magnets. When a bar of diamagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of strong magnetic field to a weaker magnetic field. We also observe that the magnetic field lines are expelled or repelled by the diamagnetic material, and the magnetic field inside the material is reduced. Let us discuss the causes of diamagnetism. We know that the orbiting electrons around the nucleus in an atom are equivalent to the current-carrying loops. These electrons possess an orbital magnetic moment. For a diamagnetic material, the resultant magnetic moment of all the electrons in an atom is zero. When the diamagnetic material is placed in an external magnetic field, due to induced current, the movement of the electrons for which the orbital magnetic moment is in the same direction as that of the external magnetic field is slowed down, and the orbital magnetic moment of the electron decreases. Likewise, the movement of the electrons for which the orbital magnetic moment is in the opposite direction to that of the external magnetic field is sped up, and the orbital magnetic moment of the electron increases. The material then develops a resultant magnetic field in the direction opposite to that of the external magnetic field. Hence, the diamagnetic materials are repelled by the external magnetic field. Although diamagnetism is present in all materials, its effect is very weak in most of them. Some examples of diamagnetic substances are bismuth, copper, lead, silicon, and nitrogen at STP. Magnetic susceptibility of the diamagnetic substances is greater than or equal to -1 and less than 0. Relative magnetic permeability of these substances is greater than or equal to 0 and less than 1. Superconductors exhibit perfect diamagnetism. When a material is cooled below its transition temperature, it becomes a superconductor. In superconducting state, the material behaves as a perfect conductor of electricity and a perfect diamagnetic material. When a material makes a transition from the normal state to the superconducting state, it actively excludes the magnetic field from its interior and hence repel magnets. This is called Messner effect. Maglev trains, or in other words, magnetically levitated superfast trains, work on the same principle. Let us discuss about paramagnetic materials. Paramagnetic materials are the materials that are weakly attracted by the magnets. When a bar of paramagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of weak magnetic field to a stronger magnetic field. The magnetic field lines get concentrated in the paramagnetic material, and the magnetic field inside the material increases. Now let us discuss about the causes of paramagnetism. In case of paramagnetic material, individual atoms possess a permanent magnetic dipole moment due to the orbiting electrons in the atom. But, due to random thermal motion of the atoms, the net magnetic moment of the material is zero. When a paramagnetic material is placed in an external magnetic field of induction B0 at low temperatures, the magnetic dipole moment of the individual atoms align in the same direction as of the external magnetic field. Some examples of paramagnetic materials are aluminium, sodium, calcium, etc. Magnetic susceptibility of paramagnetic materials is small and positive. Relative magnetic permeability of these materials is slightly greater than 1. A paramagnetic material placed in an external magnetic field gets weakly magnetized. The magnetization of the paramagnetic material is inversely proportional to its absolute temperature. That is, I is inversely proportional to T. Let this be equation 1. The magnetization is directly proportional to the applied magnetic induction. That is, I is directly proportional to B0. Let this be equation 2. By combining equations 1 and 2, we get I is proportional to B0 by T. This equation can be written as I is equal to C into B0 by T, where C is the proportionality constant. Let this be equation 3. We know that B0 is equal to mu0 H. Let this be equation 4. We also know that the ratio of magnetization to magnetic intensity is magnetic susceptibility. That is, chi is equal to I by H. Let this be equation 5. Substituting equation 4 and 5 in equation 3. And on simplification, we get chi is equal to C into mu0 by T. This is known as Curie's law, where C is called Curie's constant. Let this be equation 6. Thus, the magnetic susceptibility chi depends on the nature and the temperature of the material. Since the magnetization of a material is directly proportional to the applied magnetic field induction and inversely proportional to its absolute temperature, the magnetization of a material increases up to a certain level by increasing the magnetic field and decreasing the temperature. At this magnetization, all the atomic dipoles are aligned in the same direction of the magnetic field. This value of magnetization is known as saturation value and is represented as IS. Beyond this value, Curie's law is not applicable. Let us now discuss about ferromagnetic materials. Ferromagnetic materials are the materials that are strongly attracted by the magnets. When a bar of ferromagnetic material is placed in a non-uniform external magnetic field, it has a strong tendency to move from a region of weak magnetic field to a stronger magnetic field. And the field lines are highly concentrated inside the ferromagnetic material. Let us discuss the causes of ferromagnetism. Similar to the paramagnetic material, the individual atoms in a ferromagnetic material also possess a permanent magnetic dipole moment due to the orbiting electrons. These individual atoms interact with one another and arrange themselves in a common direction over a volume of some millimeters. This volume is called the domain. Each domain contains about 10 to the power 11 atoms, and each domain has a net magnetization. The magnetization changes from domain to domain. Thus, the net magnetization of a ferromagnetic material is negligible. When a bar of ferromagnetic material is placed in an external magnetic field of induction B0, the magnetization of the domains orient in the direction of the applied magnetic field. When the external magnetic field is removed, some ferromagnetic materials can retain the magnetization, and such materials are called hard ferromagnets or hard magnetic materials. Alnico, steel, Ticonal, etc. are the examples of hard ferromagnetic materials. These materials are used to prepare permanent magnets. There are some other materials which can lose its magnetization when the external magnetic field is removed. These materials are called soft ferromagnetic materials, and they are used to prepare temporary magnets. Iron, cobalt, nickel, etc. are the examples of soft ferromagnetic materials. The magnetic susceptibility of ferromagnetic materials is positive and very much greater than 1. The relative magnetic permeability of these materials is also positive and very much greater than 1. Now, let us discuss an activity to know the effect of temperature on ferromagnetism. Let us consider an L-shaped wooden stand and fix a strong magnet on top of it. Consider a ferromagnetic material, say, a nickel paper clip tied to a string which is fixed at the base of the wooden stand. Let the paper clip be suspended in air with the help of a magnet as shown. Now, heat the clip with a lighter to increase its temperature. At a particular temperature, the paper clip falls down. That is, at that temperature, the clip transforms from being ferromagnetic to paramagnetic. This transition temperature is known as Curie's temperature. In other words, the temperature of transition from ferromagnetic to paramagnetic is called Curie temperature and is denoted by Tc. The magnetic susceptibility above Curie's temperature, which is in the paramagnetic phase, is given as chi is equal to C by T minus Tc. This table lists out Curie's temperature of some ferromagnetic materials. Let us now discuss about hysteresis of a ferromagnetic substance. The relation between the magnetic field induction B and the magnetic intensity or applied magnetic field H is complex and is often non-linear. To understand this, consider an unmagnetized ferromagnetic material in the core of a current-carrying solenoid. Let us see the magnetic behavior of the ferromagnetic material through one cycle of magnetization by plotting a graph with H on the x-axis and B on the y-axis. When the current passing through the solenoid increases, the magnetic field in the core of the solenoid H also increases. As a result, the magnetic field strength B in the ferromagnetic material placed in the solenoid also increases. This is represented by the curve OP in the graph, which shows the alignment and merger of domains, and no further enhancement is possible after this. By reducing the current through the solenoid, the applied magnetic field H decreases to 0. When H is equal to 0, the magnetic field strength in the ferromagnetic material B is not equal to 0, and this is represented by the curve PQ in the graph. And the value of B at H is equal to 0 is called retentivity or remanence. Now increase the current through the solenoid in a direction reverse to that of the previous one. Thus, certain domains in the ferromagnetic material are flipped until the net field inside it stands nullified. This is represented by the curve QR in the graph. This magnitude of applied magnetic field H is known as coercivity. As the current in the reverse direction increases in magnitude, we once again obtain the saturation magnetization in a direction opposite to that of the previous one. This is represented by the curve RS in the graph. Again, decrease the magnitude of current in the reverse direction such that the applied magnetic field H also decreases and becomes 0. But the magnetic field strength in the ferromagnetic material is not 0. This is represented by ST in the graph. Again, decrease the magnitude of current in the reverse direction such that the applied magnetic field H also decreases and becomes 0. But the magnetic field strength in the ferromagnetic material is not 0. This is represented by ST in the graph. And finally, increase the current in the original direction. Then again, the magnetic domains in the ferromagnetic material flipped until the net magnetic field inside it becomes 0. The magnetic field thus increases in the original direction. This is represented by TU in the graph. With any further increase in current through the solenoid, the applied magnetic field in it and the magnetic field strength in the ferromagnetic material increases to its saturation value. This is represented by UP in the graph. We can observe that the curve OP does not retrace itself, as the magnetic intensity or applied magnetic field H is reduced. Hence, we can say that for a given value of magnetic intensity H, magnetic field B depends on the previous history of the sample. This phenomenon is called hysteresis. Magnetic flux is the physical quantity that gives the measure of the strength of a magnetic field over a given area. Magnetic flux is defined as the number of magnetic field lines passing through a given area in a magnetic field. The magnetic flux, phi, is equal to B dot A, which is equal to BA cos theta, where B is the strength of the magnetic field. A is the area of the given surface through which the field lines pass, and theta is the angle between the direction of magnetic field and the area vector. Let this be equation 1. The SI unit of magnetic flux is Weber, and its CGS unit is Maxwell. Maximum magnetic flux passes through a given area when the area vector and the magnetic field are in the same direction. That is, the angle between the plane of the given area and the magnetic field is 90 degrees. The angle between the area vector and the magnetic field theta is equal to 0 degree. Cos 0 degree is equal to 1. Thus, the magnetic flux phi is equal to BA. When the flux passing through a given area is maximum, the magnetic flux passing per unit area is called magnetic flux density. Then, the magnetic flux density B is equal to phi by A. Let this be equation 2. Now let's discuss about Gauss' law for magnetism. We know that Gauss' law for electrostatics is derived from Coulomb's law. From Coulomb's law of electrostatics, we derive that the electric field strength E is equal to 1 by 4 pi epsilon naught into Q by R square. Let this be equation 3. Gauss' law for electrostatics states that the electric flux passing through a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. That is, integral over the closed surface E dot ds is equal to Q by epsilon naught. Here, integral over the closed surface E dot ds is the electric flux, and Q is the total charge enclosed by the closed surface. Let this be equation 4. Similarly, Gauss' law for magnetism can be derived from the definition of magnetic field strength. We know that the magnetic field strength B is equal to mu naught by 4 pi into m by r square. Let this be equation 5. By observing the Gauss' law for electrostatics, we can write Gauss' law for magnetism as integral over a closed surface B dot ds is equal to mu naught times the net pole strength enclosed by the closed surface. Here, integral over the closed surface B dot ds is the magnetic flux, and m is the total pole strength enclosed by the closed surface. Since the isolated magnetic pole or magnetic monopole does not exist, that is, the magnetic dipoles alone exist with the poles that are opposite in nature, the net pole strength enclosed by the closed surface is 0. Now we can write Gauss' law for magnetism as integral over the closed surface B dot ds is equal to 0. Let this be equation 6. Let's discuss Gauss' law for electrostatics and magnetism more explicitly by considering the field lines due to an electric dipole and a magnetic dipole. Consider a closed surface that encloses one of the charges of an electric dipole, and another closed surface which encloses one of the poles of a bound magnet. In case of an electric dipole, the electric field lines begin on the positive charge and end on the negative charge. That is, the electric field lines are not closed loops. They are open curves. Here, the electric field lines go beyond the closed surface. Thus, a non-zero electric flux exists in a closed surface. The electric flux is equal to 1 by epsilon naught times the charge enclosed by the closed surface. On the other hand, the magnetic field lines due to a magnetic dipole are directed from north pole to south pole externally and south pole to north pole internally. That is, the magnetic field lines are continuous closed loops. Here, the number of magnetic field lines going beyond the closed surface is equal to the number of magnetic field lines entering into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is 0. For a better understanding, let's discuss Gauss' law for magnetism with some examples, such as a solenoid and a toroid. In the case of a current-carrying solenoid, the magnetic field lines around the current-carrying solenoid are similar to that of the magnetic field lines due to a magnetic dipole. Here, the magnetic field lines come out from one face of the solenoid and enter into its other face. Let's consider a closed surface around one face of the solenoid. Then, the number of magnetic field lines going out of the closed surface is equal to the number of magnetic field lines coming into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is equal to 0. In our other example, that is of a toroid, the current-carrying toroid produces a magnetic field at its core in circular loops. Now, consider a closed surface around a point of the toroid. As the magnetic field lines due to the current-carrying toroid are continuous closed loops, the number of magnetic field lines going out of the closed surface is equal to the number of magnetic field lines coming into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is equal to 0. Magnetic flux is the physical quantity that gives the measure of the strength of a magnetic field over a given area. Magnetic flux is defined as the number of magnetic field lines passing through a given area in a magnetic field. The magnetic flux, phi, is equal to B dot A, which is equal to BA cos theta, where B is the strength of the magnetic field. A is the area of the given surface through which the field lines pass, and theta is the angle between the direction of magnetic field and the area vector. Let this be equation 1. The SI unit of magnetic flux is Weber, and its CGS unit is Maxwell. Maximum magnetic flux passes through a given area when the area vector and the magnetic field are in the same direction. That is, the angle between the plane of the given area and the magnetic field is 90 degrees. The angle between the area vector and the magnetic field theta is equal to 0 degree. Cos 0 degree is equal to 1. Thus, the magnetic flux, phi, is equal to BA. When the flux passing through a given area is maximum, the magnetic flux passing per unit area is called magnetic flux density. Then, the magnetic flux density, B, is equal to phi by A. Let this be equation 2. Now let's discuss about Gauss' law for magnetism. We know that Gauss' law for electrostatics is derived from Coulomb's law. From Coulomb's law of electrostatics, we derive that the electric field strength E is equal to 1 by 4 pi epsilon naught into Q by R square. Let this be equation 3. Gauss' law for electrostatics states that the electric flux passing through a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. That is, integral over the closed surface E dot ds is equal to Q by epsilon naught. Here, integral over the closed surface E dot ds is the electric flux, and Q is the total charge enclosed by the closed surface. Let this be equation 4. Similarly, Gauss' law for magnetism can be derived from the definition of magnetic field strength. We know that the magnetic field strength B is equal to mu naught by 4 pi into m by r square. Let this be equation 5. By observing the Gauss' law for electrostatics, we can write Gauss' law for magnetism as integral over a closed surface B dot ds is equal to mu naught times the net pole strength enclosed by the closed surface. Here, integral over the closed surface B dot ds is the magnetic flux, and m is the total pole strength enclosed by the closed surface. Since the isolated magnetic pole or magnetic monopole does not exist, that is, the magnetic dipoles alone exist with the poles that are opposite in nature, the net pole strength enclosed by the closed surface is 0. Now we can write Gauss' law for magnetism as integral over the closed surface B dot ds is equal to 0. Let this be equation 6. Let's discuss Gauss' law for electrostatics and magnetism more explicitly by considering the field lines due to an electric dipole and a magnetic dipole. Consider a closed surface that encloses one of the charges of an electric dipole, and another closed surface which encloses one of the poles of a Baum magnet. In case of an electric dipole, the electric field lines begin on the positive charge and end on the negative charge. That is, the electric field lines are not closed loops. They are open curves. Here, the electric field lines go beyond the closed surface. Thus, a non-zero electric flux exists in a closed surface. The electric flux is equal to 1 by epsilon naught times the charge enclosed by the closed surface. On the other hand, the magnetic field lines due to a magnetic dipole are directed from north pole to south pole externally and south pole to north pole internally. That is, the magnetic field lines are continuous closed loops. Here, the number of magnetic field lines going beyond the closed surface is equal to the number of magnetic field lines entering into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is 0. For a better understanding, let's discuss Gauss' law for magnetism with some examples, such as a solenoid and a toroid. In the case of a current-carrying solenoid, the magnetic field lines around the current-carrying solenoid are similar to that of the magnetic field lines due to a magnetic dipole. Here, the magnetic field lines come out from one face of the solenoid and enter into its other face. Let's consider a closed surface around one face of the solenoid. Then, the number of magnetic field lines going out of the closed surface is equal to the number of magnetic field lines coming into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is equal to 0. In our other example, that is of a toroid, the current-carrying toroid produces a magnetic field at its core in circular loops. Now, consider a closed surface around a point of the toroid. As the magnetic field lines due to the current-carrying toroid are continuous closed loops, the number of magnetic field lines going out of the closed surface is equal to the number of magnetic field lines coming into the closed surface. Thus, the net magnetic flux enclosed by the closed surface is equal to 0. The Earth is a natural source of magnetism. The strength of the Earth's magnetic field varies from place to place on the surface of the Earth. The magnitude of the Earth's magnetic field strength is of the order 10⁻⁻⁵ Tesla. The actual cause of the Earth's magnetic field is not yet known. As of now, it is believed that the Earth's magnetic field is caused due to the convective motion of metallic fluids in the outer core of the Earth. Iron and nickel form the major components of the fluids in motion. The convective motion of these fluids gives rise to electrical currents, which in turn give rise to the Earth's magnetism. This is known as the dynamo effect. The Earth's magnetism can be realized by its magnetic field lines. The Earth's magnetic field lines are similar to the magnetic field lines of a magnetic dipole. Hence, we can assume a magnetic dipole to be placed at the center of the Earth. However, the axis of the hypothetical magnetic dipole assumed at the center of the Earth does not coincide with that of the geographic axis of the Earth, about which it rotates. The angle between the axis of the dipole and the geographic axis of the Earth is approximately 11.5 degrees. From the observation of the Earth's magnetic field lines, we can see that the magnetic poles are located where the field lines due to the dipole enter or leave the Earth. A magnetic pole is located at latitude of 79.74 degree north and a longitude of 71.8 degree west. This is a place in North Canada. This pole, which is near the geographic North Pole, is called the North Magnetic Pole. Earth's magnetic field lines enter the Earth near this pole. Another magnetic pole is located at latitude of 79.74 degrees south and longitude of 108.22 degree east, a place in the Antarctica. This pole, which is located near the geographic South Pole, is called the South Magnetic Pole. Earth's magnetic field lines leave the Earth near this pole. When compared with the magnetic field lines of a bar magnet, this nomenclature of the magnetic poles of the Earth's magnetic field creates confusion. This is because, for the bar magnet, the field lines enter the magnet at its south pole and leave the magnet at its north pole. Whereas, for the Earth, the field lines go into the Earth at its north magnetic pole and come out of the Earth at its south magnetic pole. The convention for this nomenclature for the Earth's magnetic field arose due to the fact that the north pole of a freely suspended bar magnet points towards the geographic north, whereas the south pole of the magnet points towards the geographic south. The north pole of a magnet was named so because it is a north-seeking pole. Similarly, the south pole of a magnet was named so because it is a south-seeking pole. We know that like poles repel and unlike poles attract. Thus, in reality, the north magnetic pole of the Earth behaves like a south pole and the south magnetic pole of the Earth behaves like a north pole. To completely describe the magnetic field at any point on the surface of the Earth, we have to specify its three elements at that point, namely declination, d, angle of dip or inclination, I, and horizontal component of the Earth's magnetic field, HE, let us study about these three elements in detail, one by one. First, the declination. We all know that the Earth is spherical in shape. On this spherical surface, we can draw an infinite number of imaginary circles passing through the Earth's geographical north and south poles. All these circles have one common diameter, which is the line joining the geographical north and south poles, or the Earth's axis of rotation. These imaginary circles are called longitudes. Each of these circles, along with the Earth's axis of rotation, can be drawn in one plane. This plane is called the geographic meridian. The geographical meridian, when viewed from top, appears to be a straight line. Similarly, we can obtain the magnetic meridian by drawing a line from the magnetic north and south poles. This magnetic meridian also looks like a straight line when viewed from the top of the chosen point. At any given point, the geographical meridian and the magnetic meridian together look like two intersecting straight lines. The acute angle between these two straight lines is known as declination. It is denoted by the capital letter D. Declination changes from place to place on Earth. Declination is minimal at the equator and goes on increasing with latitude. The second element of the Earth's magnetic field is the angle of dip or inclination. A magnetic compass needle is provided with a pivot such that it can rotate freely about a vertical axis. The needle comes to rest when aligned with the magnetic meridian to indicate the magnetic north. If the needle were also provided with a pivot such that it can rotate freely about a horizontal axis, it would also rotate in the magnetic meridian plane. If the compass is placed in the northern hemisphere, its north end dips down from the horizontal position. If the compass is placed in the southern hemisphere, its south end dips down from the horizontal. The angle through which it dips with respect to the horizontal plane at that point is known as the angle of dip or the inclination, denoted by the capital letter I. In other words, inclination is the angle that the total magnetic field of the Earth, BE, makes with the horizontal surface of the Earth at a given point. The inclination is 0 at the equator and increases as the latitude increases. If this compass is placed atop the magnetic pole, it will come to rest in the vertical position. We can measure the inclination at any given point using a magnetic needle with a horizontal axis and a spirit level. The study of these elements help us to find the total magnetic field of the Earth, BE. To find BE at any point on the Earth, we take the help of the third element, the horizontal component of the Earth's magnetic field, HE, at that point. BE and HE are vectors. Let us now construct the vector diagram using all the three elements. Locate point P on the globe at which you want to determine the Earth's total magnetic field, BE. Draw a circle passing through the point P and the geographic north and south poles. This is the geographic meridian circle. Draw another circle passing through the point P and the magnetic north and south poles. This is the magnetic meridian circle. Draw a plane which is tangential to the sphere at point P. Draw a tangent PA to the geographic meridian circle at point P. PA lies on the tangent plane and represents the geographic north-south direction. Draw a tangent PB to the magnetic meridian circle at point P. PB also lies on the tangent plane, but represents the magnetic north-south direction. Construct a parallelepiped passing through P, A and B. Rotate the line PA in the tangent plane such that it touches the parallelepiped at B. This angle of rotation is the angle of declination D at the point B. The length of the line PB, to some scale, represents the magnitude of the horizontal component, HE, of the Earth's magnetic field at the point B. Rotate the line PB in the vertical plane such that it touches the parallelepiped at C. This angle of rotation is the angle of dip, I, at the point P. The line PC represents the magnitude and direction of the total magnetic field, BE, at the point P. Drawing this three-dimensional diagram is a cumbersome process. Instead, we can draw a two-dimensional view of the essential elements to determine the Earth's total magnetic field. Take only the plane represented by PBCD in the three-dimensional view and draw a two-dimensional view of triangle PBC. Draw a horizontal line PB with the arrowhead at B. The length of this line, to some scale, represents the magnitude of HE. Draw a line PC making an angle I with PB. Draw a line BC is perpendicular to the line PB with an arrowhead at C. Line BC represents the vertical component VE of the Earth's magnetic field. On the line PC, put an arrowhead at C. Line PC represents the total magnetic field BE of the Earth at the point P. We can now write the trigonometric relationships for the sides and the angle in the right-angled triangle. Sin I is equal to BC divided by PC, which is equal to VE divided by BE, or VE is equal to BE sin I. Cos I is equal to PB divided by PC is equal to HE divided by BE, or HE is equal to BE cos I. Tan I is equal to BC divided by PB is equal to VE divided by HE, or VE is equal to HE tan I. Let us start with some general facts related to magnets. A freely suspended bar magnet oscillates for some time and then comes to rest along the magnetic meridian in the direction of geographic north and south. One end of the magnet points to the geographic north pole, called north-seeking pole or north pole of the magnet, and the other end points to the geographic south pole, called south-seeking pole or south pole of the magnet. This is because the Earth behaves as a huge bar magnet with its magnetic north pole located near the geographic south pole. and with its magnetic south pole located near the geographic north pole. We know that the like poles of two magnets repel each other and the unlike poles attract each other. Thus, the north pole of the magnet is attracted by the Earth's magnetic south pole and vice versa. If a bar magnet is broken into two pieces, we get two similar magnets with a decrease in the magnitude of their properties. Thus, the magnets always exist in dipoles. Isolated magnetic monopoles do not exist. This implies that isolated magnetic north pole or south pole does not exist. Let us now discuss an activity about the magnetic field lines of a bar magnet. Consider a glass sheet with some iron filings sprinkled on it. Bring the bar magnet from the bottom of the glass sheet close to the sheet. As the magnet is brought close to the glass sheet, we observe that the iron filings on the sheet arrange themselves as shown. If we draw lines along the orientation of the iron filings, the lines will represent the magnetic field lines. Similar field lines are observed in the case of a current-carrying solenoid and an electric dipole. Let us now learn about the properties of magnetic field lines around a bar magnet. The field lines of a magnet start from the north pole and end at the south pole externally, which is outside the magnet. But internally, that is inside the magnetic field lines start from the south pole and end at the north pole. Thus, the magnetic field lines of a magnetic dipole are continuous closed loops. In the case of an electric dipole, the electric field lines start from the positive charge and end at the negative charge. Unlike magnetic field lines, the electric field lines are not closed loops. They are open curves. The field lines give us a visual impression of the magnetic field. If we draw a tangent to a magnetic field line at a given point, it represents the direction of a resultant magnetic field at that point. The magnetic field lines never intersect each other, because the resultant magnetic field at a point has only one direction. If we assume that two magnetic field lines intersect at a point, then the resultant magnetic field at that point would have two different directions, which is not possible. The magnitude of magnetic induction, which gives the strength of the magnetic field, is obtained by the number of field lines passing normally through a given area. If the number of field lines passing normally through a given area is large, then the field is considered to be strong. It is similar to strength of an electric field. If the number of field lines passing normally through the area is less, then the magnetic field is considered to be weak. An alternative method of plotting the field lines of a magnetic dipole is as follows. Take a bar magnet, which is nothing but a magnetic dipole, and place it on a sheet of paper, which is placed on a horizontal surface. Then place a small magnetic compass at the north pole of the magnet. Plot a point on the paper indicating north of the compass needle. Shift the compass such that the south of the compass needle is observed at the plotted point. Then, again plot another point at the north of the compass needle, and then shift the compass as done earlier. Repeat the process to plot different points on the sheet around the magnet, and note down the orientation of the compass at each position. We observe that the series of points plotted on the sheet are directed from the north pole of the magnet to its south pole. By connecting all the points, we get the magnetic field lines due to the magnetic dipole. The direction of the compass at different points on the field lines gives the direction of magnetic field at that point. Let us now learn the similarities between a bar magnet and a solenoid by comparing the magnetic induction of both. Finite number of continuous turns of a conducting wire wound in a helical shape represents a solenoid. We learnt earlier that the magnetic field lines of a bar magnet are similar to the field lines of a solenoid. Hence, a bar magnet can be assumed to be the same as a large number of current-carrying loops placed adjacent to each other. The two faces of the solenoid are similar to the poles of a bar magnet. The field lines leave one face of the solenoid into its exterior, and hence, this face of the solenoid is like the north pole of the bar magnet. The field lines enter the solenoid at the other face, and hence, this face is like the south pole of the bar magnet. Thus, the magnetic field lines of a solenoid are continuous closed loops similar to the field lines in the case of a bar magnet. We learnt earlier that if a bar magnet is cut into two pieces perpendicular to its length, two small bar magnets are formed. Similarly, if a solenoid is cut perpendicular to its length into two parts, two solenoids of smaller length are obtained. The two solenoids produce weak magnetic fields around them. Thus, each smaller solenoid acts like a small bar magnet. To make it more clear that the field due to a solenoid is similar to that of a bar magnet, we calculate the magnetic field induction B at a distant point on the axis of the solenoid and compare with the magnetic field induction at a point on the axial line of a bar magnet. Consider a solenoid of finite length with n turns per unit length. Let A be the radius, 2L be the length, and I be the current passing through the solenoid. Let the solenoid be placed such that the axis of the solenoid is along the x-axis of the coordinate system, and its center coincides with the origin. Then, the left end of the solenoid lies at the position -L, and its right end at +L. Let us consider a point P on the axis of the solenoid, and let R be the distance from the center of the solenoid to that point. To calculate the magnetic field induction B at the point P on the axial line of the solenoid, consider a small element of the solenoid of thickness dx, located at a distance of x from the center of the solenoid. Then the distance of the point P from the small element of the solenoid is r minus x. As n is the number of turns per unit length, the number of turns in the small element of the solenoid is equal to number of turns per unit length into length of the small element of the solenoid. That is equal to n into dx. We learnt earlier that the magnetic induction B on the axis of a current-carrying circular loop at a distance x from the center of the loop is equal to mu naught Ia square by 2 into x square plus a square whole power 3 by 2. Thus, the magnetic induction due to the current passing through the small element of the solenoid at the point P on the axial line, dB, is equal to mu naught n dx Ia square by 2 into r minus x square plus a square whole power 3 by 2. The total magnetic induction due to the solenoid can be calculated by dividing the total length of the solenoid into number of small elements, and by integrating the magnetic inductions due to all the small elements, we get the total magnetic induction due to the solenoid. When we consider the small elements of the solenoid from one end to the other, the distance of the elements from the center of the solenoid varies from -L to L. Thus, the total magnetic induction at the point P due to the solenoid is B is equal to integral -L to L dB. That is equal to integral -L to L. Mu naught N dx IA square by 2 into R minus X square plus A square whole power 3 by 2. But IAN and mu naught are constant. Hence, the magnetic induction B is equal to mu naught N IA square by 2 into integral -L to L dx by R minus X square plus A square whole power 3 by 2. When we consider the point on the axis of the solenoid at a large distance, R is much greater than A and R is much greater than X. Hence, we neglect the terms A and X in the denominator of the expression for B. Then, B is equal to mu naught NIA square by 2 into integral -L to L dx by R cube. But the distance of the point P from the origin R is constant. Thus, B is equal to mu naught NIA square by 2R cube into integral -L to L dx. On integrating and substituting the limits, we get the magnetic induction B is equal to mu naught NIA square by 2R cube into 2L. By multiplying the numerator and denominator of the expression with pi and rearranging the terms in the expression, we get the magnetic induction B is equal to mu naught by 2 pi into Ni2L pi A square by R cube. We learnt earlier that a current-carrying loop behaves like a magnetic dipole, and its dipole moment is given by M is equal to I into A, where A is the area vector of the loop. The solenoid consists of n number of loops per unit length. I is the current through the solenoid, and A is the radius of each loop. Thus, area A of each loop of the solenoid is pi into A square. The total number of loops in the solenoid is n into 2L, and hence the magnetic moment of the solenoid M is equal to N2LIA, which is equal to N2LI pi A square. Substituting M for the terms in the expression for magnetic induction B, we get the magnetic induction B is equal to mu naught by 2 pi into M by R cube. On multiplying the numerator and denominator with 2, we get the magnetic induction B is equal to mu naught by 4 pi into 2M by R cube. This is the same expression that is used to find the magnetic induction at a distant point from the center of a bar magnet on its axial line. Thus, a current-carrying solenoid and a bar magnet produce similar magnetic fields. Therefore, a solenoid is equivalent to a bar magnet, and their magnetic moments are also equal. If the magnitude of the induction they produce at given distant points from their centers on their axial lines is equal. The Earth abounds with a variety of elements and compounds. In addition, we have seen different types of alloys, compounds and elements. To classify these substances based on their magnetic properties, let us discuss the basics of magnetic properties. We know that matter is made of atoms, and atoms are made of electrons and nuclei. We have seen that a circulating electron in an atom has a magnetic moment. The resultant magnetic moment of an atom is the vector sum of the magnetic moments of all such circulating electrons in the atom. Here, the magnetic moments of these atoms in an object are randomly oriented and their net magnetic moment is 0. When the object is placed in an external magnetic field, the magnetic moments of the atoms are aligned partially or completely in the direction of the applied magnetic field. Then, the net magnetic moment of the object is in the direction of the external magnetic field. Thus, the net magnetic moment per unit volume is called magnetization or intensity of magnetization. That is, I is equal to m by v. The unit for intensity of magnetization is ampere per meter. Its dimensional formula is m0, L-1, T0, A1. When an object is placed in an external magnetic field, the total magnetic field inside the object is the sum of the applied magnetic field and the magnetic field due to the magnetization of the object. To discuss this more explicitly, let us consider a long current-carrying solenoid, where B0 is the magnetic field in the interior of the solenoid due to the current passing through it. When a magnetic material is inserted into the solenoid, the material gets magnetized. In such cases, the total magnetic field inside the material is the sum of magnetic field due to the current-carrying solenoid and the magnetic field due to the magnetization of the material. That is, B is equal to B0 plus Bm, where B is the total magnetic field inside the material, B0 is the magnetic field due to the current-carrying solenoid, and Bm is the magnetic field due to the magnetization of the material. Let this be equation 1. The magnetic field due to the magnetization of the material is directly proportional to its intensity of magnetization. That is, Bm is directly proportional to I. This equation can be further written as Bm is equal to mu0 into I, where mu0 is the magnetic permeability of vacuum. Let this be equation 2. Now let us introduce a new vector quantity called magnetic intensity, denoted by H, where H is equal to B by mu0 minus I. Let this be equation 3. The units and dimensions of magnetic intensity are the same as that of intensity of magnetization. That is, the SI unit of H is ampere per meter, and its dimensional formula is m0, L-1, T0, A1. On rearranging the terms in equation 3, we get the total magnetic field inside the material B is equal to mu0 into I plus H. Let this be equation 4. Now, the total magnetic field inside the material is redefined in terms of I and H. That is, the external magnetic field applied on the material, represented by H, and the magnetic field due to the magnetization of the material, represented by I. The contribution due to the magnetization of the material I is influenced by factors such as the nature of the material to be magnetized and the applied magnetic field. It can be expressed as I is equal to chi into H. Let this be equation 5, where chi is a dimensionless quantity called magnetic susceptibility. It depends on the nature of the material, which represents the degree of magnetization in response to an external magnetic field. The value of magnetic susceptibility is small and positive for paramagnetic materials. It is small and negative for diamagnetic materials. Substituting equation 5 in equation 4, we get the total magnetic field inside the material B is equal to mu naught into chi h plus h. That is, B is equal to mu naught into 1 plus chi into h. Let this be equation 6. But the magnetic susceptibility and relative magnetic permeability are related as mu r is equal to 1 plus chi. Hence, in place of 1 plus chi, we can write mu r, and we can further write equation 6 as B is equal to mu naught into mu r into h. Let this be equation 7. We know that the relative magnetic permeability is the ratio of the magnetic permeability of the material to the magnetic permeability of vacuum. That is, mu r is equal to mu by mu naught. Then, mu is equal to mu naught into mu r. On substituting the magnetic permeability of the material mu in equation 7, we get the magnetic field as B is equal to mu h. Let this be equation 8. The three quantities, magnetic susceptibility, magnetic permeability, and relative magnetic permeability, are related to each other, and only one of them is independent. If one of these values is given, the other two values can be determined easily. Let us have a look at the magnetic susceptibility of some elements at 300 Kelvin given in the following table. Here, it can be seen that in the case of diamagnetic substances, the value of magnetic susceptibility is small and negative. And in the case of paramagnetic substances, the value of magnetic susceptibility is small and positive. First, let us learn about magnetic compass. A magnetic compass, or compass needle, is used to find the direction of a magnetic field at a given point in a horizontal plane. It essentially consists of a magnetic needle, which is placed on a pivot in the horizontal plane. Thus, a magnetic compass can move only in a horizontal plane. When the magnetic compass is placed in a horizontal plane on Earth's surface, it aligns itself along the direction of the horizontal component of the Earth's magnetic field at that point. Or, it can be said that the needle aligns itself along the magnetic meridian at that point. At some places, the deposits of magnetic materials inside the Earth cause the magnetic compass to deviate from the magnetic meridian. At such locations, the angle of declination at that point helps us to determine the actual direction of the north. Let us now discuss the deflection of a magnetic compass placed at either of the two magnetic poles of the Earth. At the poles, the magnetic field lines either converge or diverge vertically. Hence, the horizontal component of the magnetic field is negligible. This means that the needle can effectively point in any direction. Thus, in terms of the path-finding ability, the compass is rendered useless at the poles. In such cases, a dip circle is useful. Dip circle is basically a magnetic needle pivoted in such a manner that it is free to move in a vertical plane. We can thus measure the angle made by the magnetic field with the horizontal plane. In the case of poles, this needle points downward, and as it approaches the equator, the needle aligns in the horizontal direction. Let us now discuss about the Earth's magnetic field. The Earth's magnetism is largely attributed to iron and nickel ions present in the hot and molten core of the Earth. This theory gains force from the fact that the Moon does not have a molten core, and hence it does not have a magnetic field. Venus has a slower rate of rotation and a weaker magnetic field compared to Jupiter, which has the fastest rate of rotation and a very powerful magnetic field. Although magnetism is attributed to these circulating currents in the core of the planets, the energy required for sustaining these currents and the causes for this is not very well understood till date. These are still interesting research topics. In fact, the path of the solar wind, that is, the stream of charged particles emitted from the sun, produces some magnetic field, which interacts with the Earth's magnetic field. Therefore, you can say that the Earth's magnetic field influences the solar wind. The pattern of the Earth's magnetic field is noticeably different at the poles than from the rest of the Earth. In fact, there is evidence that the Earth's magnetic field changes prominently in the short term, which is in centuries, and long term, which is over a span of 1,000,000 years. The dip angle at London varied by 3.5 degrees in a span of 240 years. That is, from 1580 to 1820 AD. This indicates that the position of the Earth's magnetic poles varies its position with time. Hence, it is observed that the Earth's magnetic field has even reversed the direction during long-term changes. Let's begin with permanent magnets. Permanent magnets are substances that can retain its ferromagnetic property for a long period of time at room temperature. Let's discuss the properties of a material used for making a permanent magnet. We cannot make permanent magnets from all types of materials. The hysteresis curve helps us to select a suitable material for it. The material should have high retentivity in order to retain its magnetization for a long period of time and increase the strength of the magnet. The material should have high coercivity so that it does not lose the magnetic property during temperature fluctuations. Unwanted or scattered magnetic fields and minor mechanical damage. Also, the material should have a high relative magnetic permeability so that it can be easily magnetized. Thus, taking into consideration of all the properties, steel is the most suitable choice. The other suitable materials are alnico, cobalt steel, and Ticonel. There are different methods of making permanent magnets. In method 1, we can prepare a permanent magnet by holding a steel rod in the north-south direction and hammering it repeatedly. This is an age-old method of magnetization. In method 2, hold the steel rod and rub it with one end of a bar magnet repeatedly in a particular direction. Thus, a permanent magnet is formed. This method of magnetization is known as single touch method. However, the most efficient method of making a permanent magnet is to place a suitable magnetic material in the core of a solenoid and pass direct current through it. Thus, the magnetic field due to the current-carrying solenoid magnetizes the material placed in the core of the solenoid. This method of magnetization is known as electrical method. Permanent magnets have many applications, such as in magnetic door stoppers and magnetic screwdrivers. Now let's discuss the making of electromagnets. The materials used in electromagnets should have high magnetic relative permeability and low retentivity. However, the hysteresis loop for this type of material is narrow. Considering all these properties, soft iron is the most suitable material for making electromagnets. Place a soft iron rod in the core of a solenoid and pass current through it. The magnetism of the solenoid increases by many times due to the soft iron rod in the core of the solenoid. When the current through the solenoid is switched off, the magnetism due to the solenoid is also switched off because of low retentivity of soft iron. Thus, the electromagnets are referred to as temporary magnets. Electromagnets have their usage in many applications, such as electric bell, loudspeakers, and telephone diaphragms. Huge electromagnets are used in cranes to lift bulk quantities of iron, steel, and machinery.